Okay, so for our last part of this chapter, we're going to look at some applications of thermal processes, okay, in our day-to-day lives. So just to apply the concepts of conduction, convection, and radiation in everyday examples. So before we start on these examples, I think I want to introduce a very simple structure with which we can use to understand these examples and also to answer our questions. So there are four steps we should always consider. Okay, step one, which way is heat flowing? Step two, what method is heat flowing with? So conduction, convection, or radiation. Step three, do you want to increase or decrease this rate of heat transfer? And step four, how are we going to do it, okay, in order to achieve step three? So let's start with our first example, and I'll show you how we use this framework. So in a hair dryer, okay, first step, which way is heat flowing? So we want to heat up some air, which means that within the hair dryer, there should be a heating element. There's something that warms up. So heat is flowing from the heating element within the hair dryer to the air that is being passed through it. Next, what method is heat flowing? Okay, it is going to be through conduction because it is a solid heating element transferring heat to the air that is in contact with it and that is being blown through it. Three, do we want the rate of heat transfer to be fast or slow? We want it to be fast, right? Because we want the air to come out very warm in order to dry the hair quickly. Four, how can we achieve high rate of heat conduction? Okay, so putting that all together, you can see that to get a high rate of heat conduction, you need a metal heating element because metal with its free electrons are a very good conductor of heat. Additionally, you also want as much surface area as possible because a large surface area means that there can be a lot of contact between the heating element as well as the air passing through it in order to transfer the heat quickly. So our next example, the instant water heater. Okay, so similar to the hair dryers, what is going to happen is instead of heating up air, we're heating up water for showers or for use in day-to-day applications around the household. So which way is heat flowing? Same thing from the heating element to the cool water that is coming into the heater. What method? Again, conduction, because it is going from the solid heating element to the water. Do we want the rate of heat transfer to be fast or slow? We want it to be fast. And how can we achieve it? Same thing as the hair dryer, except this time it's to a liquid. Okay, but that doesn't make a difference. We still want a metal with free electrons as that's a good conductor. And we also want a large surface area so that there's a lot of contact and the heat can be conducted from the heating element to the water. So you can see over here in the diagram, that is what's happening. Next one, thermal wear. Okay, so in a cold country, people wear clothes to keep themselves warm. So which way is heat flowing? Okay, so from the hotter object to the colder object, heat will be flowing from the person to the surroundings. What method is heat flowing? Okay, there is going to be conduction and convection, okay, but also radiation. But radiation is generally very little compared to conduction and convection because the person is not going to be very, very warm. Okay, we don't consider a person, a temperature, body temperature to be very warm, unlike fires or the sun, which are in thousands of degrees. Okay, so do we want the rate of heat transfer to be fast or slow? So to keep yourself warm, okay, and transfer heat, we know that the heat transfer goes from the body to the external surroundings. We want to slow down the heat transfer. So how can we achieve, okay, slowing down conduction and convection? So you can see in this slide over here, okay, you have porous materials like down fibers and microfibers. They trap tiny pockets of air. So since the air is trapped, there is no convection current because the air is not able to circulate around. Okay, it might get warmer, it might get less dense, it might try to rise, but it's stuck by this layer. So therefore, there's very little convection, we've reduced the rate of heat transfer via convection. Similarly, okay, because the particles in air are very far apart, okay, the collisions happen much less frequently than in a solid or liquid. The air is going to be a insulator. It is a poor conductor of heat. So the same thing also happens to conduction. Okay, the rate of heat loss due to conduction is reduced. So by trapping the air, okay, not allowing the air to flow around, we reduce convection. And also by trapping the air, we create a layer of an insulator to reduce conduction. So these are the methods by which, okay, the thermal wear is able to keep a person warm in a cold climate. Next, a double or triple glaze window. Okay, so what is a purpose of the windows? It's to keep the homes, okay, comfortable, cool in hot climates. So which way? Step one is heat flowing. Okay, heat must be flowing therefore from the environment into the house. Two, what method is heat flowing? Okay, we've got conduction, we've got convection, and we also have radiation happening. So do we want the rate of heat transfer to be fast or slow? Okay, we want to keep a temperature difference, right? We want to make sure that the house remains cool, even though the outside environment is very hot. So we are trying to reduce the amount of heat transfer. So how do we do that? How do we reduce conduction, convection, and radiation? So first thing, okay, you see these double or triple glazed windows, what they do is they have two or three pieces of glass, okay, with air in the middle. So as mentioned in the previous example, air is a poor thermal conductor. So as an insulator, you trap the air in between, you are reducing the rate of conduction. Okay, the next one, because it's a very thin layer, you also make it very hard for convection to occur. Okay, because if the air is allowed to travel freely in a large space, then you might get some convection currents. But when you trap it between two glass panes, very narrow glass panes, okay, you're not going to get a lot of convection. And next, radiation. Okay, because the glass is smooth and shiny, it is going to be a poor absorber of radiation. So that means that you also reduce radiation. So the design of this reduces both conduction and convection as well as radiation in order to keep the houses cooler. Next, an electric kettle. Okay, so which way is heat flowing? Okay, so step one, heat must be flowing from the kettle to the water. Step two, what method, okay, is heat flowing? So heat must be flowing in both conduction, because okay, it is a heating element touching the water, and in convection because the water is stuck in the kettle. Unlike okay, the heater and the hair dryer where the fluid is being pumped through it. Over here, the liquid is left in the kettle, okay, as it heats up. So there is both conduction and convection. Three, do we want the rate of heat transfer to be fast or slow? We want it to be fast, right? So, in order to boil the kettle quickly. So, how do we achieve all this? Okay, what we first make sure is let's increase the rate of conduction. So, just like the hair dryer, just like the the water heater, we want a metal heating element, large surface area with free electrons, so conduction is very quick. Second, in order to increase the rate of convection, we want to make sure that the kettle has a design where convection currents can occur. So in order to do that, the heating element must be at the bottom. Okay, earlier in this chapter, I gave an example of putting a heating element on top. Let's say you blow torch the top of water. You won't form a convection current because the water, being less dense and hot, is already at the top. Okay, then it would not create a convection current. So you want your heating element to be at the bottom. So you can see over here in the diagram, it is at the bottom. And also there is a large enough space for the convection current to occur. You cannot have a very narrow, thin kettle that would make it hard for convection current to form. So this design allows the kettle to increase the rate of conduction and convection. In addition to that, okay, a very minor point, we actually don't want the kettle to transfer heat to the surroundings too quickly. So we do not want it to radiate heat too quickly. And another way that can help is by having the kettle be silver and shiny in its surface, because that makes it a poor emitter of radiation. So that means that whatever heat, okay, that the heating element is providing to the water is not being lost to the surroundings very, very quickly, so that the water can boil more quickly. Next one, a hot air balloon. So it's not about getting the hot air balloon off the ground. That is a question about density, but it's about heating the air inside the hot air balloon. So where do we want our heat to flow? From the burner to the air inside the hot air balloon. Okay, what method is the heat flowing? Right now you are heating air, so it's going to be convection. Okay, next, do we want the rate of heat transfer to be fast or slow? We want it to be fast, right? So that we can heat up the air inside the hot air balloon quickly. So how do we do that? Okay, we make sure that the burner is at the bottom of the hot air balloon, okay, and we trap the hot air inside the balloon so that, okay, you can have a convection current to quickly heat up the air inside the hot air balloon. But once, okay, the air inside the hot air balloon is hot and your hot air balloon is less dense than the air around it and it's rising, okay, you also want to make sure that you keep the air hot. So that is why the material of the hot air balloon is also made of cloth, which is a poor conductor of heat, so that the heat inside does not get transferred to the surroundings too quickly. So you can actually see that what's happening is there are parts where you want heat transfer to be fast and parts where you want heat transfer to be slow, and different processes as well that you want to be fast or slow. So it can be quite complicated, and you need to really be very careful and think about what is the most likely scenario, okay, where you want your heat transfer to be fast, where you want your heat transfer to be slow. So the next one, okay, this is not whether you want to or not, but some examples of a sea breeze. If you've taken geography, you might actually recall some of this. So during the day, we know that what happens is land heats up faster compared to the sea. So what happens is that the air above the land will heat up and rise, whereas the air above the sea is not as hot, so it remains cooler. But once the air above the land rises, okay, it leaves behind an area of lower pressure, and the air above the sea rushes in to take its place. So that is why we have a sea breeze. Okay, the breeze comes from the sea, okay, and this leads to a convection current, because once the air from the sea comes in, it is heated up once it's over the warmer land. And then it will rise, and then this process will repeat over and over again, creating a sea breeze, okay, in the daytime during the mornings. Now at night, the same thing happens but in reverse. Okay, just as how the land heats up faster than the sea, it also cools down faster than the sea. So after sunset, the sea is actually warmer than the land, and the air above the sea will heat up and rise. And this creates lower pressures above the sea, and the air that is cooler and denser over land will rush to take its place, causing a land breeze from land to sea. Okay, and after it goes above the warmer water, it will heat up, rise, and repeat this process again. Okay, so you typically get land breezes after sunset and sea breezes just after sunrise. Okay, now greenhouses. Okay, so the crops require a warm climate for growth, but in a colder country, this may not be possible many months in the year. So which way is heat flowing? Okay, it's flowing from the sun to the earth. Okay, and what method? It's radiation. Okay, and do we want the rate of heat transfer to be fast or slow? So this one is also interesting as well. Okay, because you do want the heat transfer to be fast from the sun to the greenhouse, but you want the heat transfer from the greenhouse to the environment to be slow. So how do we achieve this? Number one, okay, we make sure that the greenhouse is a good absorber of radiation, so it is made of clear materials, okay, where the infrared radiation can pass through the glass. And then once its infrared radiation passes through the glass and heats up whatever is inside the greenhouse, okay, the air, the plants, the floor, we want to make sure that this heat remains inside the greenhouse. So in that case, we must make sure that from the greenhouse to the environment, there is very little conduction and convection. So that is why the greenhouse is usually insulated by glass and there is very little air movement. Okay, it's sealed in so that you can't have convection currents forming, warmer air cannot escape. Okay, and then end up cooling the greenhouse until the plants are not in a suitable environment anymore. Okay, another example is a space blanket. So you might have seen some of these before, okay, to keep someone warm. So which way is heat flowing? Okay, if somebody is very, very cold, okay, and they are in a cold environment, which way do you want heat to flow? Okay, or which way is heat flowing naturally from the person to the environment? They're still losing heat. Okay, and what's the method? We have conduction, convection, and radiation, okay, all being in play here. And do we want the rate of heat transfer to be fast or slow, right? If the person is already very cold, okay, you want to slow down the heat transfer because they're losing heat to the environment and you don't want them to keep losing this heat to the environment. So how can we reduce the conduction, convection, and radiation? Okay, so one way is with a blanket, because with a blanket, this means that you trap some air, so you reduce conduction and convection, right? Just like our triple or double glazed windows. But at the same time, this space blanket, being made of a shiny and smooth surface, is going to be a poor emitter of heat. So you also reduce radiation as well. Okay, the person is going to not radiate as much heat to the environment once you cover them with something shiny and smooth compared to their clothes, which might be a darker color. It may be made of a rough material. So besides people, okay, you can also use this to protect houses against bushfires because it is a poor absorber of infrared radiation as well. But in this case, okay, the heat transfer is from the fire to the house and you still want to slow it down. So that is why you can use something shiny and smooth as a poor absorber of radiation to ensure that the transfer of heat from the fire to the house is minimized as much as possible. Okay, and then we've got an example of global warming. Okay, so in climate change and global warming, what is happening? You might have heard of greenhouse effects or greenhouse gases. Okay, so just like the greenhouse earlier, okay, you can think of Earth as a giant greenhouse because radiation is absorbed by the ground, okay, or by the sea, and then as this radiation, okay, gets absorbed, the ground and the sea warm up and also emits their own radiation out into space. However, with greenhouse gases, okay, it acts as kind of an insulation because it prevents some of this radiation from escaping. It actually absorbs the radiation and reflects some of it back down to Earth. Okay, so the natural greenhouse effects actually keeps the Earth at a livable surface temperature. Without the natural greenhouse gases or natural amounts of greenhouse gases that were released before the Industrial Revolution, okay, Earth would actually have a surface temperature below freezing. So that little bit of carbon dioxide that we do have in the atmosphere does actually help. Okay, however, because of the additional greenhouse gases, okay, the additional carbon dioxide and methane and other types of greenhouse gases we release due to the industrial actions that we take, okay, more and more radiation is getting trapped by these greenhouse gases, less is escaping into space. So that means that the global temperatures have increased significantly over the past 200 years since the Industrial Revolution. So let's look now at our worked examples. Okay, describe and identify how the energy transfer processes are relevant in each of these daily situations. So hair dryer, a pot of soup, and a blanket to keep warm. Okay, we've already gone through them earlier, so I'm not going to spend too much time. So for a hair dryer, heat is transferred from the heating element to the air by conduction. For the pot of soup, okay, the heat is transferred from the flame to the pot by conduction and by radiation. And then from the pot to the soup, it is transferred by conduction. And then within the soup, it is convection. Lastly, the blanket. Okay, the blanket reduces the rate at which conduction happens because it traps air, a poor conductor of heat, around the body. This also reduces the rate of convection because the air is unable to form a convection current. Next one, how does vacuum flask keep the hot coffee within it hot? So now let's apply, okay, our four-step process. Step one, which way is heat flowing? Okay, the coffee being warmer than the surroundings will want to transfer heat to the surroundings. So heat will be transferred one way. And then what method is heat flowing? Okay, we've got conduction, convection, and radiation going on all at the same time. Our third step, do we want it to increase or decrease? Okay, if we want to keep the hot coffee hot, we want to decrease the rate of heat transfer so it takes a longer time before it reaches thermal equilibrium. And how do we do this? In step 4. Okay, so first, to reduce conduction, the flask is double walled and between the walls is a vacuum. Okay, so in a vacuum, there's no particle, so no conduction can occur. So where can conduction occur? Only through the lid and some of the supports, okay, which are minimized. So the lid itself is also made of an insulating material, and so are the supports. So to reduce convection, you got an airtight lid, so the convection currents, okay, will not form in the air above it, just like in the coffee cup example earlier on in this chapter. And lastly, to reduce radiation, the walls of the flask are silver and shiny because they are poor absorbers and poor emitters of radiation. So they're not going to warm up and they're not going to give off much radiation. Okay, so that's how we break down this full question, okay, step by step. Of course, okay, you don't need to write so much once you get a hang of things, but right now I'm showing you every single step to make it much clearer for you to think about how we want to structure an answer.
Now we're going to show that water is a poor conductor of heat. What I have here is a Bunsen burner, a retort stand, a boiling tube clamped vertically in it, a basin of ice, some water, and a small piece of wire gauze. I'm going to place an ice cube into the boiling tube. Follow it with a piece of wire gauze and add some water. Now I'm going to tilt the boiling tube at an angle. I'm going to move the Bunsen burner and heat the top of the boiling tube. The reason the piece of wire gauze is placed in there is to keep the ice at the bottom of the tube. If that wasn't there, the ice would just simply flow to the top. Now we can see that the water at the top of the boiling tube is boiling, while the ice still remains at the bottom. Heat transfer doesn't occur between here and here. That shows us that water is a poor conductor of heat.
So as you see in this video over here, okay, you can have very dramatic effects as long as you appropriately, okay, design your setup or your device in order to increase or decrease the heat transfer that is going on. So over there, we just saw that we wanted to reduce, okay, the amount of heat transfer. And actually, water is not a very good conductor of heat compared to, let's say, a piece of metal. And because it was heated from the top, there's no convection current formed. And even though the water at the top was boiling, okay, the bottom of the boiling tube containing the ice cube was still cold enough that the ice cube remained solid. Of course, given enough time, okay, the whole container will get warm enough and the ice would melt and eventually all the water would boil. But for the purposes of the video, okay, this demonstration shows that it is actually possible for the top of the boiling tube to be so hot that the water is boiling, while at the bottom, okay, it is at 0 degrees, the ice is still solid and hasn't yet melted. So we've come to the end of this chapter. Okay, I hope it's much clearer now. Okay, and if you need any further time, okay, just like any of the other videos, please feel free to go back to the section where you need more time to understand, to repeat a little bit more, or you can play it a bit slower as well.